Now we'll talk about the oxygen and CO2. So oxygen means O16. So O16 which is having a spin of 0. Similarly CO2 also having a spin of 0. Okay, so how the rotational Raman spectra will look for CO2 and oxygen. First we'll talk about CO2. So this is ray line having a delta J equals to 0. Okay, now here we have one line, then I am showing this is dotted line, and then we have second line, and for the next one is dotted line, then another line. And similarly here I am showing one line and followed by dotted line, then one line followed by dotted line, one line. So now this will be right, 0 to 2. It's very simple, no need to get confused. After everything is done, it will be very clear. So 1 2 3, and then 2 to 4, and 3 to 5, and this will be 4 to 6, and here it will be j plus 2 to j, 2 to 0, 3 to 1, 4 to 2, 5 to 3, and 6 to 4. Okay, so this is Stokes lines and this is anti-Stokes lines. Okay, so for CO2, okay, for CO2 every level with odd J value is missing. Means what it means? So whatever line I have shown here, dotted line, so this is 6 beta, this is 10 beta, sorry B, 14B, 18B, and 22B. Similarly 6B, 10B, 14B, 18B, and 22B. Okay, for CO2, this is for CO2. For CO2, energy level with the odd J value is missing. Means whatever the dotted line I have shown here, they are missed transitions. Okay, so here instead of this 10B, so we'll see directly transition from 6B to, I'm just saying that this energy level is missing. If a transition happened from here to here, that means 6B to, so no, like that I cannot say. How to say completely this. Okay, so for CO2 molecules, the energy level with odd J value is missing, only even J value is are observed, values are observed. So this is 0, even value observed, this is 1, odd, not observed, this is 2, even, observed, and this is 3, odd, not observed, and this is 4, even, observed. Okay, so now the important thing is here. So now the distance, first point is a distance between, we can call as a distance or separation. Okay, distance or separation, distance or separation between two Stokes lines and anti-Stokes lines will be 8B. Just wait for a second. Sorry for disturbance. My Wi-Fi is going to stop. I'm just connecting through my laptop. Okay, so now the difference between the separation between the two Stokes lengths and anti-Stokes lengths will be 8b centimeter inverse. Whereas when we see the rotational Raman spectrum here, in this case the separation between two lines is 4b everywhere, but in this case it is a 8b. So why it's 8b? Because whatever transitions we have with the odd, okay, so whatever odd transition, odd values we have, so that is not existing here. That means, so there is no 10b, we have only 6b and 14b. So what is the difference between 6b and 14b? That is 8b. And similarly we don't have 18b because this is odd. And now what is the difference between 14b and 22b? Again 8b. And similarly we don't have 10b here because one is odd, so the difference will be here 8b, and similarly from here to here 8b. Okay, now the second point is that the separation between first Stokes and first anti-Stokes will be 12b. So I am saying that from here to here 6 plus 6 12. So this is about the CO2. Now we will go for oxygen. Okay, so for oxygen it's quite opposite. Okay, for oxygen even J values will missing, and only odd J values we will observe. Okay, that means I think it's better to make another diagram. This is delta J equals to 0. Okay, this is even, odd, and from next even, odd, next even. Similarly even, odd, even, odd, even. This will be 6b, 10, 14, 18, 20. All are negatives. Stokes length will be negative, and this positive 6b, 10, 14, 18 and 20. So this is from 0 to 2, and this is 2 to 0. So 1 to 3, 2 to 4, then 3 to 5, 4 to 6, 3 to 1, 4 to 2, this will be 5 to 3, this will be 6 to 4. So this is for oxygen. For oxygen even J value is missing, only odd J value is observed. So now 2 points we need to see. So what is the difference between the separation between two Stokes and anti-Stokes? Separation between Stokes and anti-Stokes. Two Stokes lengths and anti-Stokes lengths. So now this is not existing, even number is not existing, only odd number is existing. That means only 10, 18 is existing here. If you see the difference between these two, this will be 8 centimeter inverse, 8b centimeter inverse. And similarly here this one. Okay, so this is same in CO2 also. We have a 8b centimeter inverse, but this will change. The separation between the first stroke and second stroke, sorry, the separation between first stroke and first anti-strokes, this will be change. So this comes out to be 20b, because here first stroke is 10, because 6b is not existing, because this is even, and the second stroke will, so first anti-stroke will be 10, so 10 plus 10 will be 20. So this is for CO2 and oxygen. For CO2, odd is absent. For O2, even is absent. Okay. Now we'll go for the this CO2 and oxygen is example for the which is having a nuclear spin of 0. Now we'll go for the nuclear spin which is having a 0 or sorry non-zero. We have for a nuclear spin non-zero. Now we have nuclear spin is not equals to 0. So we have two examples, H21 and N214. Okay, so when we have a nuclear spin of 0, that time the energy levels got missed. Sometimes even, sometimes odd, but in this case we will not see any energy level missing from the spectra. Here we will see only change in the intensity, changes in the intensity. So for 14 nitrogen spectra we will see lines in the ratio of 2:1. For hydrogen we will see a 3:1. So what is this 2:1 and 3:1? See, this is for nitrogen, this is delta J equals 0, this is for Rayleigh scattering, Rayleigh line. So 2:1 means the first line is 2, the second line is 1. The first line is 2 means 6b line. Okay, now this is 2, so next line, that is 10b, that should be 1. The ratio between 6b and 10b should be 2:1. Okay, this is done. And now next line will be a bigger line, that is minus 14b. These are all a negative charge. And now next line will be 18b, minus 18b, so that should be a 1:2 with this, that means less. Next line will be a 22, minus 22b, so that will be even more higher. And next which will come here, minus 26, so that will be a 1:2 of this one. Now so this is 0 to 2, next 1 to 3, 2 to 4, 3 to 5, 4 to 6, 5 to 7. Okay, so there is a, I said that for nitrogen the ratio is 2:1. That means the first line will be 2, the second line will be 1, and again the first line will be 2, the second line will be 1, again first line will be 2, the second line will be 1, like that. And same with the anti-strokes, this will be more and this will be less, and this will be 2, 1, 2, 1, like that. So this is for the nitrogen. In other words, we can say even J values are more intense. Even J value having energies, energy transitions are, we can say even J values are more intense compared to odd. Here we can see this is the 0 even intense, 1 odd less intense, 2 even intense, 3 odd less intense, like that. And for hydrogen we have a 3:1 ratio. the same spectra, it will, here we see in a 2:1. For hydrogen we will see 3:1. But one thing here we need to see, the separation between any line will be a 4b, I mean between two Stokes lines and two anti-Stokes lines, and this separation will be 6b. But when we are talking about the compounds, the molecules which are having a nuclear spin of 0, in that case this will changes. It will comes out 8b, sometimes it comes to be 12b, sometimes like in case of oxygen this comes out to be 20b, in case of CO2 it comes out to be 12b. Okay, so when they will ask a problems for oxygen and nitrogen, that time these values will be useful, and this spectra also useful. And this is about the rotational Raman spectra, and tomorrow I will be collecting some of the problems, so I will be solving those problems, and whatever we discussed till now, they are for the linear top molecules. And we'll go next for other tops. We have 4 tops in the rotational spectra. So linear, spherical, symmetric, and antisymmetric. So this is done. So for spherical top molecules, these are like whatever the like spherical top means, we can take octahedral shape. Okay, so any axis you take, just take this axis. If you rotate this axis, it will not produce any change in the polarizability. All spherical top molecules are rotational inactive, so that's why the rotational Raman spectra is not applicable for spherical top molecules. And for symmetric top and asymmetric top, we cannot discuss the rotational Raman spectra because of their complexity. So the rotational Raman spectra is mainly applicable for only linear molecules. So that too, the molecules which are having greater than 3 atoms, for them rotational Raman spectra is not that much, means not applicable, because again if it is carbon dioxide, the number of atoms are 3, so rotational Raman spectra is applicable here. So some molecules which are having a the number of atoms are greater than 3, so for them we cannot explain so like H2O2, HCN and CO2. So for these molecules we can explain the rotational Raman spectra, but when we have more than 3 atoms, I think the complexity is the reason why we can't use rotational Raman spectra for molecules which are having more than 3 atoms. Okay, yeah, we can see that complexity, if more than 3 atoms are there, the complexity, I think only complexity I am thinking, but I have read somewhere that rotational Raman spectra is not applicable for atoms which is having more than 3 atoms, like we can take H2SO for this kind of things. Okay, so this is about the rotational Raman spectra theories and everything, and only problems are left. I will be making a separate videos on the problems what they have asked in a previous exams like CSR, GATE exam. And I hope this video is clear. So if you have any doubts about this, you can comment in the comment box, and if you like my video, please subscribe to my channel. Thank you.